Okay, so Chapter 12, Section 1, Sequences and Series. So, sequences and series notation. So we're going to cover what is a sequence, what are sequences, describe recursively defined sequences, then look into the partial sums of sequences, and then sigma notation for sequences. Okay. So roughly speaking, a sequence is an infinite list of numbers. The numbers in the sequence are often written as a sub 1, a sub 2, a sub 3. The dots mean that the list continues forever. Okay, so it's a list of numbers that could be, let's look at some examples. So for example, it could be the numbers 5, 10, 15, 20, 25, right? So clearly we're adding 5s every time. It could be a list where there is no reasonable pattern, right? It could be something like 3.12, 7.98, then negative 3.21, then positive 21.19. Right, so here is this list, and there is no reasonable pattern that I can think of. Maybe there is some reason for this madness of how you go from one number to the other, but at the moment there doesn't seem to be one, and that's okay. A sequence doesn't have to have a pattern to establish how you go from one to the other. It's simply a list of numbers. That list goes on forever, so we indicate these little dots to show that, oh, this keeps going. It's not just going to stop there. But what's important is that the order matters. It's not just that these numbers are on the list. It's important that this one is the first number on my list, and this one is the second number on my list, and this one's the third one, and then this one's the fourth one, right? So the order of the numbers makes a difference, and then often these are separated by commas just to make sure that it's clear that one number is ending and the other one is beginning. Okay, so there is an order to them. So when we refer to a list, and then we want to talk about the first one on the list, right? How do we use math language to indicate that it's the first one on my list, the second one on my list? What if I want to talk about the third one on the list? Blank third. So that's where we introduce these variables, and it could be any letter, but A is a very popular one to use. And so a sub 1 is just indicating that it's the first value on my list, right? This little sub-index here, this little 1, is indicating that it's the first one on my list. A sub 2, a sub 3, and so on, right? The nth one on my list is the a sub nth one, right? We can also use any other letter, b sub 1, b sub 2, b sub 3, dot, 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 dot. Right? And then because I'm using a different letter, this would be used to note that this is one sequence and this is a different sequence because I'm using a different letter, different variable to identify it. Good? Good? Okay, so obvious, like I said, there doesn't have to be a pattern from one number to the other. Or maybe it's an unknown pattern, and that might be what we're trying to figure out. How do we figure out a pattern to these numbers? But obviously when there is a pattern, especially an easy pattern or a well-established pattern, then there's more interesting things that we can do with it, right? If there is no pattern at all, then we're kind of stuck. There's really not much else we could do. But if there is a pattern, like there was one here, then we can work with that and come up with a formula that helps describe those patterns, right? So in this case, we were going from 5 to 10, 10 to 15, 15 to 20, right? So it looks like we were adding 5 every time. That's one way to look at it. Adding 5 every time. Add 5 every time to get to the next one. Okay, that's one way to look at the pattern. The other way to look at the pattern is to try and look at the relationship between the location, which is these little numbers, right? It's the second one on my list. It's the third one on the list. It's the fourth one on the list. So look at the relationship between the location and the value on that list. And so if you notice, the second one on the list, if we multiply it by 5, we get 10. The third one on the list, if we multiply it by 5, we get to 15. The fourth one on the list, if we multiply it by 5, we get to 20. And so the relationship is that the location on the list, right, when we get to the nth one on the list, then the value that goes on there is 5 times n. Good. And so that's where this little formula comes from. Good. Any questions? Any questions? So some sequences can be expressed by a formula like this. And when they can, that's very useful. Right? We can use that formula to find different values on my list. So I can say, find the 113th number on the list, and I know that that's pretty easy. It's just 113 times 5. That'll be the one that's on the list. Any questions so far on what a sequence is? A sequence is a list of numbers that goes on forever, and the order is important. We list them. The first one on the list, the second one on the list. We often say, because they're in order and we can count them, the first one, the second one, the third one on the list, we often say it's a list that's indexed by the natural numbers or the counting numbers. Right? So that's another way to describe what a sequence is. A sequence is a list of numbers indexed by the counting numbers. Right, and by indexed we mean this, that the counting numbers can identify them in a particular order. The first one on the list, the second one on the list, third one on the list, the fourth one on the list, and that just goes on by forever. Good. Any questions at all on what a sequence is? No? No. Okay. So here's some more descriptions on it. So any ordered list of numbers can be viewed as a function whose input values are 1, 2, 3, and whose output values are the numbers on the list. So we define a sequence as follows. Right? So a sequence is a function A whose domain is the set of natural numbers. The terms of the sequence are the function values A1. So this looks a little weird, right? We're used to using the letter F as a function, but here they're using the letter A as a function. Right? So it might look a little weird that way. You can also think of it as F of 1, right? Because we're used to seeing a function in terms of the letter F. F of 1, F of 2, F of 3, dot, 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 dot. Right? And so F of 1 means that the first one on the list is whatever this output is. The second one on the list is whatever the output of this function is. The third one on the list, and so on and so forth. Right? So like maybe, for example, if F of n equals to n squared plus 1, then this is the formula that's describing my sequence. So now I can plug in a 1 for n equals to 1, and I would end up with 1 squared plus 1 for the first one on my list, which is going to be equal to 2. And then 2 squared plus 1, which is going to be equal to 5. 5. Then the third one on the list, 3 squared plus 1, is going to be equal to 10, comma, and then dot, 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 and then it's kind of silly that we use the same letter, but then we'd say the nth one on my list would be n. F of n is out there, and then it is n squared plus 1, so we could say comma n squared plus 1. Good. Questions, questions, questions? No. Okay, so this notation of A1, A2, A3, this notation is the same as F of n. And also, instead of writing A of n equals to n squared plus 1, right, same thing as that one, then we also often adopt the new notation of a sub n, like this, instead of a of n. Good, which is what they describe here. Good. So a sub 1 is the first term on our sequence. The second term is a sub 2, the third term is a sub 3, and so on and so forth. Right? Not every sequence has a perfect little formula to describe it, but like I said, it's very useful when there is a nice formula and we can do more work with it when we have the formula. Sometimes the exercise will be to find that formula if you can. Good. Any questions? So far, we're good? Good. Okay, so here's some examples. Find the first 5 terms and the 100th term of the sequence defined by each formula. Okay, so remember, this is a function. This is a function. Go away. Why is this thing highlighted? This is a function where the input is the counting numbers. So if you want to find the first one on the list, you got to let n equal to 1. If you want to find the second one on the list, you got to let n equal to 2, and so on and so forth. Okay, so let's create a little table here and find a few of these values. Let's get rid of that thing there. So when n equals to 1, this first one will lead to 2 times blank minus 1. This next one will lead to, let's call this a sub 1. C sub 1 will be blank squared minus 1. And then t sub 1 will be equal to blank over blank plus 1. And r sub 1 will be equal to negative 1 to the power of blank all over 2 to the power of blank. Okay, so here we're letting n equal to 1, so it'll be 1 there, a 1 there, a 1 there, a 1 there, and a 1 there. Okay, so this will be 2 minus 1, so a sub 1 is going to be equal to 1. And then c sub 1 would be equal to 0. 1 squared is 1 minus 1 is 0. This becomes 1 over 2, so t sub 1 is equal to 1/2. And then r sub 1 is equal to negative 1. Oops, I forgot the other one here. 1 becomes negative 1 over 2, so negative 1/2. Good. All right, so we found the first value in each of these sequences. Now we've got to move on to n equals to 2. Find the second value. Good. Then we have a sub 2, we have r sub 2, we have t sub 2, r sub 2 equals, okay, and this one was 2 blank minus 1, blank squared minus 1, blank divided by blank plus 1, negative 1 to the power of blank all over 2 to the power of blank. And now we're going to let, well, I should have put this in red, I guess. N equals to 1, and n equals to 2, so we'll have a 2 there, 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 and a 2 there. Okay. So here we'll end up with a sub 2 equals to 4 minus 1, which is 3. C sub 2 equals to 4 minus 1, which is also 3. T sub 2 will be equal to 2 over 3. And r sub 2 equals to positive 1 over 4. Good. We'll squeeze in one more, and then we'll be close to where we want to be here. I think we can guess the rest. So n of 3. So we have a sub 3 a sub 3 is equal to 2 times blank minus 1. C sub 3 is equal to blank squared minus 1, and t sub 3 is equal to blank over blank plus 1, and r sub 3 is equal to negative 1 to the power of blank all over 2 to the power of blank. Squeeze it in a little bit. Okay, so that'll be a 3 there, 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 and a 3 there. So a sub 3 is going to be equal to 6 minus 1, which is 5. And then c sub 3 is going to be equal to 9 minus 1, which is 8. This will be equal to 3 over 4. T sub 3 will be equal to 3/4. And r sub 3 is going to be equal to negative 1 over 8. Good. Okay, so we did the first 3. So let's write down those, and then we can just finish off the rest. I think we can do those patterns. So let's copy this one. So a sub n equals to 2n minus 1. So we have that the first one is a 1, the second one is a 3, and the third one was a 5. The fourth one will be a 4 in here. That'll be 8 minus 1 is 7. The fifth one will be a 10 minus 1, which is 9. And also I begin to see a pattern here that it goes by 2s. It's all the odd ones. 1, 3, 5, 7, 9. So this is a really popular formula which identifies the odd numbers. List of odd numbers. Right? The odds are 2n minus 1, where n is the counting numbers. Good. So we also want to find the 100th term, and that's easy. All we have to do is plug in a 100 in here. Right? So if we plug in a 100 in there, we end up with 2 times 100, which is 200 minus 1 is 199. Dot, 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 and then this would be 199. Good. Questions, 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 questions? So that's good enough for an answer, or you can also sub-index them. A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, dot, 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 and this one was A sub 100. We're good? Questions, 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 questions? Okay, let's look at B. So now B, which was C sub n equals to n squared minus 1. Then the first one was a 0. The second one was a 3. The third one was an 8. Come over here. Okay. The fourth one, that's going to become from putting a 4 in here. That's going to be 16 minus 1 is 15. The fifth one will be 25 minus 1 is 24. So here's the first 5 terms, 1, 2, 3, 4, 5. And they also won the 100th term, 1, 2, 3, 4. So the 100th term is going to be equal to 100 squared. So 100 squared minus 1. So that's 100 times 100 is going to be equal to 1 with 4 zeros minus 1. 1 with 4 zeros is 10,000. So this is going to be 9,999 is the 100th term. Right? And again, you could label them if you want. The first one on my list, A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, dot, 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 over A sub 100. Any questions, any questions, any questions? No? Okay. C was n over n plus 1. And so we saw from up here that the first one was a half. First one was 1/2. Then 2/3. Then 3/4. So 1/2. and then 2/3, then 3/4, and we start to see a pattern really, but then it's not so hard to plug in the rest anyway. So there's the 1, 2, 3, so with 4, we'll end up with 4/5, and then 5/6. Good. And then dot, 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 and then the 100th one will be 100 divided by 101. Right? And so this is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and finally a sub 100. Good. Last one, D. The equation was R sub n. R sub n equals to -1 to the nth power divided by 2 to the nth power. Good. So we saw that when we put in a 1, this -1 to the power of 1 was just -1, and this stayed as a 2. So the first one on my list was -1/2. The second one on the list, the -1 raised to the power of 2, -1 raised to an even power becomes a positive, so this became 1, and 2 to the power of 2 is 4, so this became positive 1/4. The next one becomes a 3, -1 to the power of 3 becomes -1 to the 8th power, then positive 1 to the 2 to the power of 4, so this is just going to be powers of 2. 2, 4, 8, 16, -1/32, right? So I can just kind of see the pattern that's being established. And notice that this part, the -1 to the nth power, what it generates on our list is that it alternates between a negative number, a positive number, a negative number, a positive number, right? It alternates between signs when you use this. Good. Good. Okay, so this is the first one on my list, this is the second one on my list, this is the third one on my list, this is the fourth one on my list, this is the fifth one on my list, and then comma, dot, 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 and then I want the 100th one on my list. -1 to the power of 100, right? Whenever the exponent is even, it's just going to turn out to be a positive. And whenever the exponent is odd, it turns out to be a -1. Good. So this is going to be positive 1 over, now the denominator is 2 to the power of 100, right? So when it's 2 to the power of 3, you're expected to expand it out and actually multiply it. But very quickly, these numbers get really, really, really big, right? So the general guideline is that if an exponential number, when expanded, when you multiply it, it turns out to be a number that's less than 1,000, they want it to be written out, right? So this is, if you look in solution manuals or something, you'll see it written out like this. But once it reaches a value that's over 1,000, then people really embrace the convenience of expressing the number as an exponential. So we would leave it like that. Okay, so this is the 100th value on my list. Any questions at all? No questions, no questions, no questions. No questions, no questions. No, no, no. Okay, let's see what the author did. Basically the same thing. To find the first 5 terms, we substitute n equals to 1, 2, 3, 4, and 5, and then 100 to find the 100th term. Okay, so that's basically what we have as well. So some of your homework will be just this easy. A formula is given, find the first 5 terms, find the 100th term, find the 78th term, something like that. So you just have to plug it in and calculate it. So that part's easy. But then, of course, we throw in some twists and make things a little tougher. What if the sequence is given to you and instead they're asking you to find the nth term of the sequence? In other words, find a formula for the sequence. Good. So in order for us to find the nth term, it's the same thing as saying find the formula of the sequence. So for part A, luckily these aren't too bad. If you see a fraction, my recommendation, and these aren't rules that will always work, just sort of guidelines that usually work. But if you're given a sequence and you're asked to find the formula, the nth term, I would break it down into two separate parts, figuring out a formula for the numerators and then figuring out a formula for the denominators. Now when we say a formula, remember that the nth term refers to the location on the list. So what I want to do is think about this. I have 1/2 here, and what I want to do is I want to take this 1 and I want to somehow plug it into a formula, and the output of that formula should be this, right? I want a function a of 1 that equals 1/2, right? I want to be able to plug in a 1 and the output is 1/2. Good. And at the same time, I want that formula to work out such that if I plug in a 2, a sub 2, that 2 right there will result in 3/4, right? A of 2 should be equal to 3/4. Good. And so on and so forth, and so on and so forth. So this should be 5/6, and then the next one should be 7/8. Right, so one formula that generates these 4 terms when we plug in these their corresponding location values. A sub 3 and A sub 4. Okay, so how do we get 1 to map to 1 and 2 to map to 3? So I would break it down between the numerators and the denominators. And so if we notice, the numerators are all the odd numbers, 1, 3, 5, 7. From that, my best guess, just looking at the pattern, my next guess is that the next one's going to be a 9 in the numerator. Good? And then in the denominator, it looks like they're all 2s, powers of 2, or even numbers. 2, 4, 6, 8. Right? So they're not powers of 2 because 6 is not a power of 2. So we're just adding 2 every time. So it's just all the even numbers. Right? So my very best guess is that the next one is going to be 9 out of 10. Right? So by breaking these down, it seems to me that it's going to be the odd numbers divided by even numbers. So looking at just the numerators, we saw earlier that this is a way of describing the odd numbers, and this is a way of describing the even numbers, right? So when n equals to 1, right? So for this, you want to do a lot of guessing and checking. Try an equation, kind of guesstimate what the equation will be, and then come back and make sure it makes sense, right? So when n equals to 1, we'll end up with 2 minus 1, that's 1. And when n equals to 1, that equals to 2, so we end up with 1/2. Right? That does make sense. N equals, so let's put it over here. Check. When n equals to 1. When n equals to 1, we end up with 2 times blank minus 1 all over 2 times blank. And if n equals to 1, we end up with 1/2. Good. When n equals to 2, we end up with 2 blank blank minus 1 all over 2 times blank. And this is a 2, this is a 2, that makes it a 4 minus 1 is a 3 over 4, 3/4. And that does do that one, that it gives you the second one on my list. Good. Any questions, any questions, any questions? So it worked out. This is the formula. Any questions, any questions, any questions? No? So when you see fractions, very often it works to try and break it up to figure out a pattern for the numerator, a pattern for the denominator, and then write down that fraction. Now if you want, once you have that pattern, then you can also just kind of manipulate that algebraically and get a different expression. So you could also rewrite this as 2n over 2n minus 1 over 2n, which then reduces to be a 1, which gives you 2n is equal to 1 minus 1 over 2n. I don't know, if you like seeing it this way better, then that's fine too. This will also give us the same result, right? Again, you can guess and check. If n is 1, we end up with 1 minus a half, which is half, right? When n is 2, we end up with 1/4. 1 minus 1/4 is 3/4. That also works, right? So here's another way of expressing the same answer. Any questions? Any questions? Any questions? No? No? Okay, so two different ways of expressing the same answer. This is all for part A. So this was all part A. All right, let's do part B. Part B has -2, +4. So we have -2, then +4, then -8, then +16, then -32, and so on and so forth, so on and so forth. Okay, remember, our mission is to find a way to map the fact that there's a 1, and it's the first one on the list. So I want to do something to the 1 so that I end up with a -2. And then I want to do something to the 2. The 2 is the input to my function, such that when I do something to it, the formula results in a 4. And then 2 results in a -8, and then 3 results in a -8, and 4 results in a 4. Okay, well, it's not hard to see that these are the powers of 2. 2, 4, 8, 16, right? So it has something to do with 2 to the power of the index, the counting number, the location on the list. And then the only thing that we have to be careful about is the signs. It alternates signs between a negative there, then a positive, then a negative, then a positive, then a negative. Good. And we saw in a prior example that one way to get that is to have the -1 to the power of n formula, and then just confirm that it matches all the signs. So when n is 1, we'll get a negative. That makes sense. When n is 2, we'll get a positive, because -1 to the power of 2 is equal to a positive. Okay, so that part matches. And so now that we multiply by 2 to the power of n to get the constant. Right? So here's my guess for the formula. Oh, I already used A over there, so let's use a different one. How about B? B sub n is this one. Right? So we guess and check. This is what I think it'll be. And now I check it. Check. When n equals to 1, I end up with -1 to the power of blank, 2 to the power of blank. And that'll be a 1 there and a 1 there. So that equals to -2. Okay. When n equals to +2, then we have -1 to the power of blank and 2 to the power of blank. So we get a 2 there and a 2 there. -1 squared is +1. +1 times 2 squared is 4. So this will be equal to 4. Okay. N equals to 3. We get -1 to the power of blank and 2 to the power of blank. Put a 3 here. And so now again, this becomes -1 times 8. So this becomes -8. Okay, so it's confirming that it is giving us the values we wanted. Any questions? So it's a little trickier when you're trying to find the formula. See what the author did, probably the same thing. We notice that the numerators of these fractions are the odd numbers, the denominators are the even numbers. Even numbers are of the form 2n, the odd numbers are of the form 2n minus 1. The odd number differs from an even by a 1. Right? So once we have all the even numbers for 2n, we just subtract 1 and we get to all the odd numbers. Good. Okay, so that was a sub n equals to 2n minus 1 over 2n. That worked out. And then Same thing for the other equation. Noticing that they're powers of 2 and that they're alternating signs gives us this, and then we kind of guess and check it and confirm that that is the equation, the formula for it. Any questions? Any questions so far? Okay, so as I mentioned before, there doesn't have to be a pattern. It's nice when there's a pattern, but in order for it to be a sequence, there doesn't have to be a pattern. And sometimes maybe there is a pattern, we just don't know it yet, right? Maybe we observe something in the universe and it's pumping out weird numbers, and we don't know if there's a relationship between them, but maybe that's the whole point. We're trying to figure out how do we get from one number to the other. So in some cases, there is a nice, pretty formula for it. And in some cases, there might be something that we describe as a recursive sequence. This is a sequence which is described by the values that came before it on the list, a finite number of values that came before it on the list. So, for example, well, you got to get the thing going. So let's say that it just starts at 3, right? So that part is given. Let's say the first 2 numbers are given, 3 and I don't know, 3 and 4. Given and given. We got to get the thing going. So a sub 1 is given and a sub 2 is given. Okay, but then to get to the next one, maybe the rule is that you look at the ones that came before it, and then you, I don't know, subtract them and square them. So it'll be, let's say that the rule says take 3, the 4, subtract the 3, and square it. So that gives you a 1. Good. And then the next one is going to be subtract the previous 2 in this order. So then this would be 1 minus 4 and square it. So that would be 3 squared is 9. Good. Maybe the next one then would be this one minus that one. The next one would be 9 minus 1 squared, which is 8 squared, that's 64. Good. So the rule is subtract the previous 2, right, to get the next one on the list. Subtract the previous 2 is 2 values on the lists. On the list, then square them, Right? Is it clear that that's what I was doing here? To get the next one on the list, right? So the first 2 values are given. You got to get the thing going, right? Because I can't find this number if the way to find it is to look at the previous ones on the list. And like, there is no previous ones. It's, this is the first one. So the first 2 have to get, you got to get the ball rolling. So the first number, the first 2 numbers, the first few numbers, a finite number of initial values will be given, the initial conditions. Okay, so then to find the next one, we follow the set of instructions, right? So is it clear that this is what I did? I took the previous 2 and subtracted them in this order. 4 minus 3, 4 minus 3, squared it. So that's how I got a 1. Right? To find the next one on my list, I took the previous 2 and subtracted them, 1 minus 4, and squared them. That's how I got a 9. Right? To find the next one on the list, I took 9 minus 1, squared them. I get this one. Right? To find the next one on the list, it's going to be 64 minus 9 squared. Right? So it'll be 55 squared. Clearly, this is going to grow pretty quickly. Good. Good. Okay, well, how do I describe this in math talk? Because you don't want to write down these sentences all the time. So how do I describe the exact same thing? Okay, so let's use these notation values. The third one, To find the a sub 3, I took a sub 2 minus a sub 1 and squared it. Right? That's what I did for a sub 3. A sub 3 was equal to, let me make some more room there. I guess I'll write it over here. A sub 3 was equal to a sub 2 minus a sub 1, and I squared it. Good. That's how I found a sub 3. Took the a sub 2 minus the a sub 1. Okay, to find a sub 4, let's make it a little smaller here. To find the a sub 4, I took a sub 3 minus a sub 2 and squared it. Right? That's how I got this one. A sub 3, which was a 1, minus the a sub 4. This guy is the a sub 3, is that guy. And this one was the a sub 2, that's that guy. And then I squared it. To find the a sub 5th one, I took a sub 4 minus a sub 3 and squared it. And that's how I found this one, a sub 5. Good. Okay, well then in general, if I keep going, eventually I'll find the nth one. Let's scoot over here a little bit. If I kept going, dot, 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 eventually there would be the a sub nth one over here, a sub nth one. And how do you find the value of the a sub nth one? Well, you need to know the two numbers that came before it, right? And so sticking to my notation style, right, these are the counting numbers. So if that one is the a sub n, the one that came right before it would be the a sub n minus 1 location. And the one that came right before that would be the a sub n minus 2 location value. Right? And sticking to this formula, the a sub nth value will be found by taking the one that comes right before it, the a sub n minus 1 value, minus the a sub n minus 2 value, and then squaring the whole thing. Any questions about any of this? So this is just an example of what is a recursive one. Obviously, the little rules, the little formulas will all vary, but they all have the same characteristics. It's a sequence, but instead of being able to plug in the location value, like the 4, for example, there's nothing we do to the 4 to get to the 9. I can't square it, divide it, right? There is no set rule that will allow me to map the index numbers, the counting numbers, to the value that is there in their location, right? Someone might say, well, why don't you, the rule could be to multiply the 4 times 2 plus 1. Okay, that works for this one, but that same rule does not work here. If I do the same rule here, multiply the location, 5, and multiply it times 2 and add 1, that doesn't give me 64. Right? So I need one solid rule that works for all of them, that always maps their location to the value on in that location spot. But the way I've described this one, there's no way to do that. However, there is some method to this madness. It's not just random numbers. The numbers are described by the previous values that came on the list. In this case, every nth value can be found by looking at the two values that came right before it. Right? We do something to those values. We subtract them and square them. Any questions about this example at all? No? 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 Okay, so let's look at the formal description. So some sequences do not have simple defining formulas like those in the previous examples. The nth term of a sequence may depend on some or all of the preceding terms. The sequence defined in this way is called recursive. Here's an example. Here's another example. Find the first 11 terms of the sequence defined recursively in the following way. So here the capital F is being used to describe our sequence. Right? So we already have the first two on my list. Let's put them over here. And you want the first 11? That's a long list. All right, so the first 11, I'm going to need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so that's a lot of numbers. Okay, so we have f of 1, the first one on my list, the second one on my list, the third one on my list, the fourth one on my list, the fifth one on my list, the sixth one, the seventh one, the eighth one, the ninth one, the 10th one, and the 11th one. I won't go out that far because that's a lot of work. Okay, the first couple are just given, right? That's key to any sequence defined recursively. We got to get the ball rolling because the next one will depend on previous values, so we got to get started. Okay, so here is the recursive formula given for the nth one, right? The nth one is described by taking the nth minus 1, n minus 1th value, and the f of n minus 2th value. So the one that comes right before it and the one that comes 2 spots before it. That's what that means, right? So, for example, f of 3, right? This is where n equals to 3, is equal to f of 3 minus 1 plus f of 3 minus 2. So f of 3 is equal to f of 2 plus f of 1. It means to just add the previous two values. F of 1 is a 1, f of 2 is a 1. This one and this one both map to 1s. A 1 and a 1. So f of 3 is going to be equal to 2. Good. And that's how we get to this next value up there in blue, 2. Right? So now we have the first 3 values on my list. For the sake of getting comfortable with this notation, I'll do a couple more, but it's really not necessary, right? It's a very simple recursive formula, and I'm not going to demand that you do all of this work when you eventually get to this on your test, but it's nice to be able to do it because if the formula gets really, really complicated, you're going to want to do some of this, even if it's not every little step. Okay, so f of 4 is equal to f of 4 minus 1 plus f of 4 minus 2. So f of 4 equals to f of 3 plus f of 2, right? And the f of 3, we just discovered that one. That one was a 2. And f of 2, though that's still a 1. So this is the 2, and this is this 1 right here. So f of 4 equals to 3. Good. So we'll put it over here. How about does yellow look? Probably not very good. Need to be stronger. How about like a brown? Oh. Good. I'll do one last one this way, and then we can just go crazy with the rest of them. So this f of 5 is equal to f of 5 minus 1 plus f of 5 minus 2. So f of 5 equals to f of 4 plus f of 3. Okay. F of 5 is equal to f of 4, which we just discovered as this 3, plus, and then the f of 3, which was a 2. So f of 5 equals to 5. Good. Black. 5. So there, we got the first 5 numbers now. Almost there, right? But again, you don't have to do this much crazy work every time. Sometimes the pattern is pretty easy. Just add the previous 2. So I can easily tell that the next one is going to be the sum of these 2. which is going to be equal to an 8. And the next one is going to be the sum of these two, which is going to be equal to 13. And the next one is going to be the sum of these two, which is going to be 21. And the next one is going to be a sum of these two. Right, so it's growing pretty quickly. 34. And the next one's going to be some of these two, which is 55. And the next one is 89. Any questions? I'm sorry, I didn't catch that.
How did you know F2 would have been 1 also?
Oh, it's given to you. Find the first 11 terms of the sequence defined recursively, and f of 1 is 1, f of 2 is 1.
Oh, okay. Yes, yeah, thank you.
Yeah. You know, that's a key characteristic of these types of recursively defined sequences. They got to get the ball rolling. They got to get you started with the first couple of them, maybe the first 2, the first 4, the first 5, because the next one is described by numbers that came before it. So there's no way to do it if you don't know the numbers that came before it, right? So the first few, at least one, or the first a couple of them will be given to you, and then you gotta keep going with the recursively defined sequence. Okay, so the recursively defined sequence has a big flaw in it though, right? Because if I wanted to find, if I said, okay, this is a lot of fun, keep going, you found the first 11 of them, that's a lot of fun. Let's find, I need the 100th one now. Keep going. I need to find f of 100, the 100th number on this list. Well, the only way to find that 100th number is to know the 99th and the 98th number, right? And the only way to know 99th value is to know the 98th and the 97th value. And the only way to, right? So the point is, you can't just skip to some number in the future and find that number. The only way to get there is to build up to it. So it's not as useful as the closed formula that we saw before, where you can just jump to the 100th number by plugging in 100 into the formula and out will pop out the answer. Good. So from that perspective, recursively defined sequences are inferior to sequences defined by a closed formula. So you might wonder, well, why do we work with these? Well, because we don't really have a choice, right? This isn't something we've invented. This is just something we've noticed in the universe. This is just the way it works. There are some sequences that do not have a closed formula, but do have some sort of a recursively defined formula. Now, there are some sequences that have both. You can describe it recursively, or you can find a closed formula for it, and some sequences that don't have them both. Right. So this is a very famous sequence called the Fibonacci sequence. It occurs in lots of areas of math and science and in the universe. There's some stuff that just kind of happens to follow this pattern. So it's important, useful, fun, interesting. But as far as we know, there is no closed formula for it. But, I mean, the question is there no closed formula? Like, there can never be one? Or maybe we just haven't found it yet, right? I don't know. So maybe somebody in the future discovers some awesome, great formula that maps out the Fibonacci sequence, and then, of course, that person will be rich and famous. Good? Questions? No? 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 Okay, so any questions on recursive formulas? No. Let's see what the author did. So same as what I did. So f of 3 equals to the sum of f of 2 plus f of 1. F of 4 equals to f of 3 plus f of 2. Okay? So you can slowly build out your sequence until you get to all the 11 numbers that they wanted. So this is called the Fibonacci sequence, named after the 13th century Italian mathematician who used it to solve a problem about the breeding of rabbits. Right? So breeding rabbits somehow is connected to this Fibonacci sequence, the way a group of rabbits will grow in a population. Now I think that, there's probably some tweaking that happens there. I don't think you want to start with one rabbit and one rabbit. That seems weird, because then, anyway, sorry, there's a big truck going right by my window. Anyway, so maybe like 1,000 rabbits, and then you come back in some term, sometime later, some unit of time later, you come back 1 month later, and 1,000 rabbits is still 1,000 rabbits. And you come back 1 month after that, by the third month, now you have 2,000 rabbits. So, those rabbits had babies. And then after another month, or some other fixed unit of time, you come back and now there's 3,000 rabbits, and now there's 5,000 rabbits, and now there's 8,000 rabbits, right? So the rabbit population can be modeled to grow in this way. Of course, that's without any other restraints, right? Because they'll grow in this way, say just out in nature, until they run into a problem, right? So if they run out of food, they run out of space, or a predator comes in, or a virus or something, then their population will then decrease, right? But anyway, there's a lot of things that Fibonacci sequence can be used, can be applied to. Okay, any questions at all so far then? So far we have sequences. Sequences are indexed by the counting numbers. So we have closed formulas for some of them. We have recursive formulas for some of them. Good. So you might be asked to expand the recursive formula, or you might be asked to find the recursive formula given the numbers. Okay, now let's look at the partial sums of a sequence. Something else that we might want to do, that we often want to do, particularly in calculus as we prepare to get into calculus, is that when we're given a sequence, we want to think about what happens as we begin to add them in this way. So let's say that we're given the sequence a sub 1, a sub 2, a sub 3, so on and so forth. We want to create a new sequence. A new sequence, which here we're using the letter capital S to represent this new sequence, where the first number on my new sequence is just equal to the first value on the given sequence. And then the second value in my sequence is the sum of the first two values of my original sequence. The third one is the sum of the first three and the sum of the first four, and so on and so forth. So this itself is a new sequence, but it's a sequence of partial sums. So S sub 1 is called the first partial sum, S sub 2 is called the second partial sum, and so on until we get to the S sub n is called the nth partial sum. Good. Let's expand this with a simpler problem before we get into their first example. So let's like mimic this with an example. So for example, if the original sequence, a sub 1, a sub 2, let's just say that it is the even numbers. No, let's not make even numbers. Yeah, that's fine. Let's just make it the odd numbers. So here's the sequence. 1, 3, 5, 7, 9. Right, so here is a sub 1, here's a sub 2, here's a sub 3, here's a sub 4, here's a sub 5. Right, so here is a sequence that's given. Right, that's this. And what we're going to do is we're going to create a new sequence where the first value of my sequence is equal to a sub 1. That's just going to be 1. S sub 2 is the sum of the first two on my sequence. That's 1 plus 3. That's going to be 4. S sub 3 is going to be the sum of the first three values on my sequence, which is equal to 9. S sub 4 is the sum of the first four numbers. 3 plus 5 plus 7 is equal to 16. Good. and so on and so forth. So then my new sequence is going to be 1, comma, 4, comma, 9, comma, 16, comma, dot, 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 dot. Right? So this is a new sequence. So this is S1, this is S2, this is S3, and this is S4. Good. So now the original sequence, as I presented it to you, there's a formula for this, right? It's just the odd ones. So this one is the nth value on my list is just going to be equal to, I'll just put it over here, is equal to 2n minus 1. Right? That's the nth one on my list. Good. Good, good, good. Okay, and same thing over here. There's a pattern that's happening here. The nth one on my list, way out here, the nth one on my list is, well, it's that. There's not a very easy way of describing it. It's just A1 plus A2 plus A3 plus dot, 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 all the way out to A sub n. That's what the nth one is. Okay, good, good. So the sequence of partial sums is a brand new sequence, which is defined by adding the first n numbers of an underlying sequence that's usually given to you. Good. Any questions, any questions, any questions? No? No? Okay, so let's look at another example. Find the first partial sums of the nth partial sum of the sequence given by a sub n equals to 1/2 to the nth power. Okay, so first let's begin by expanding this sequence a little bit. Let's find the first value on my list. Let's find the second one. Let's find the third one. Let's find the fourth one. Let's find the fifth one. That's pretty good, right? And then we know that the nth one is the formula. So this is 1/2 the power of n. Okay, so this one's going to be 1/2 the power of 1. This one's going to be equal to 1/2 power of 2, 1/2 to the power of 3, 1/2 to the power of 4, and 1/2 to the power of 5. Right? And so I can write it down in a more simple way this way. The first one on my list is a half, then a fourth, then an eighth, then 1/16, then 1/32, dot, 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 dot. Right? And we'll leave it alone for that. So here's my underlying sequence. Good. So now I want to find the s sub 1 value. Okay, that's just the sum of the first one. Well, that's just a half. And then s sub 2 is going to be equal to the sum of the first two. It's going to be 1/2 plus 1/4. You need a common denominator. That's going to be to multiply this by a 2 over a 2. So we'll end up with 2/4 plus 1/4, which gives you 3/4. Okay, so the second one on my list is going to be 3/4. The third one on my list is going to be equal to s sub 3 is equal to 1/2 plus 1/4 plus 1/8. Common denominator is going to be that 8, so let's multiply this by 2 over 2, multiply this by 4 over 4, and we will end up with 4 over 8 plus 2 over 8 plus 1 over 8, which then gives me 7 over 8. Good. And then finally the fourth one is said find the first 4 partial sums. The fourth one on my list is 1/2 plus 1/4 plus 1/8 plus 1/16. Right, the sum of the first 4. And the common denominator is that 1/16, so let's multiply this by 2 over 2, multiply this by 4 over 4, and multiply this by 8 over 8. And I'll have my values of s sub 4 will be equal to 8 over 16 plus 4 over 16 plus 2 over 16 plus 1 over 16, which equals to 12, 14, 15 over 16. Okay, so I already have my first four values. The first one on my new list is going to be 1/2, followed by 3/4, followed by 7/8, followed by 15 over 16. So let's write down those values. So here was my underlying sequence, a sub 1, a sub 2, a sub 3, right? And now s sub 1 is going to be equal to 1/2. That's s sub 1. S sub 2 was 3/4. S sub 2 is 3/4. S sub 3 is going to be 7/8. And finally, S sub 4 is 15 over 16. S sub 4. Okay, well, a lot of what we do in math is look for patterns, right? So a very nice little pattern begins to appear. Just based on this little pattern right here, can we do a pretty good guess of what the next one's going to be, right? Just based on this pattern. Notice that it's always the case that the numerator is 1 less than the denominator, right? 16, this one's 15. 8, this is 7. 4, this is 3. 2, this is 1. It's always 1 less. Or you can look at it the other way around. It's always 1 more. 1, and we add 1, we get to 2. 3, we add 1, we get to 4. 7, we add 1, we get to 8. So really, all you have to do is find a formula that connects its location values, the numbers, to either the numerators or to the denominators, and then you can tweak that by adding or subtracting 1 to get to your answer. Okay, so if we look at the denominators, 2, 4, 8, 16, well, that's just the powers of 2, right? So there's a nice pattern that emerges there. So I'm going to guess that the next one here is going to be equal to 2 to the power of 5 in the denominator. And that's going to get me to 32, right? Because it's powers of 2. And then in the numerator, it's always 1 less. So I'm just going to say that the numerator is 2 to the power of 5 minus 1 as well. Good. So they didn't ask for this, but this is a nice little pattern here. So why not do that? And then, well, okay, as long as you're establishing the pattern, then as we keep going, the nth one, well, the pattern is going to be that it's a fraction where we have 2 to the nth in the denominator and then 2 to the n minus 1 in the numerator. Good. Any questions? Any questions? Any questions? No, no, no. This looks weird because now this looks like a giant fraction that's all weird. So let me rewrite that this way. I don't want to write it like that. I'll just say S sub n is equal to a giant fraction where the denominator is 2 to the nth power and the numerator is 2 to the nth power minus 1. So look, we were able to get a nice closed formula for the sequence of partial sums in this case. Any questions? No? No? Okay, let's see what the author did. Find the first, okay, so we found that, and then 3/4, and then 5, 15, 16s. Notice the value partial sum, the denominator is powers of 2, and then 1 less for the numerator. Okay. So in general, the nth partial sum is exactly what I got. And then you can simplify this by breaking this up as 2 to the nth over 2 to the n minus 1 over 2 to the n. And that simplifies to this. And then we can also just map it all and see a pattern. Right, so the original values, the a sub 1, a sub 2, a sub 3, a sub 4 values, map this way, whereas the sequence of partial sums are mapping up to here. Particularly when we see it in this notation, we can see what's going to happen in the long run. Right? As n gets bigger and bigger and bigger and bigger, this denominator is going to get bigger and bigger and bigger, right? So 2 to the 8th power, 2 to the 16th power, 2 to the 20th power, 2 to the 100th power. Right? This denominator gets huge. 1 over a very large number becomes a very, very small number, right? And so as n gets really large, we end up with 1 minus a very small number. Infinitely small number. So as n gets really large, the output of this is going to become really, really close to 1. Right? So this is going to have a horizontal asymptote at y equals to 1. These outputs are going to get closer and closer and closer to 1, but never equal to 1, and it's never going to be bigger than 1. It's just going to get closer and closer and closer to 1. Does that make sense? Yes. So there will be a asymptote here. Let's see if this looks good on Desmos. See if we create a table and we have x, well, let's do n, and then we have 1 minus 1 divided by 2 to the power of n. Okay, and we start off with 1, that maps to a half, 2, that maps to 0.75, 3, then 4, then 5, 6, 7, right? Do you see how, plugging them into here, I get all these outputs, and then if I graph them, I get 1 comma 0.5, 2 comma 0.75, 3 comma 0.875, right? And so on and so forth. But they're not growing out of control. As n gets larger and larger, this part gets smaller and smaller and smaller. So as n gets larger, this output becomes closer and closer to 1. Look, at n equals to 7, it's already at 0.9928. So eventually they approach a horizontal asymptote at y equals to, what happened to the, y equals to 1, right? So these little green guys get infinitely close to that red line. And even though it almost looks like it is equal to that, it's not. If you zoom in, zoom in, zoom in, eventually you see that the green dot is not actually on the red one. Okay? And it might look like it's it. Any questions at all? Right, so that's what this is describing. S sub 1, S sub 2, S sub 3, S sub 4, S sub 5. Any questions, any questions, any questions, any questions? No? Okay, so we want to refresh our memory on sigma notation that helps us express an infinite sum. That's what a sigma notation is. So given the sequence a sub 1, a sub 2, a sub 3, so on and so forth, if we want to describe how to add the first n numbers, we can write the sum of the first n numbers using sigma notation. And that's what this is. Right? This notation means that we want to add a sub 1, a sub 2, a sub 3, a sub 4, dot, 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 dot. This tells you where you're going to begin your counter, right? So the index here is the k. So we use this little guy here, this little counter as k. And so it will change starting at 1 and ending at and including this number up here, this value up here. And it's always a sum for this notation, right? This giant sigma means it's an infinite sum. Good? Good, 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 good. Okay, so the left side of this expression is read as the sum of a sub k from k goes from 1 to k equals to n. The letter k is called the index of the summation, or the summation variable, and the idea is to replace k in the expression after the sigma by the integers 1, 2, 3, dot, 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 all the way out to n. and then add the resulting expressions, arriving at the right-hand side of the equation. Good. So this giant sigma tells us to add, the k tells us where to begin, k equals to 1, the k equals to n tells us where to end. Be careful because it doesn't always have to start at 1. It could be a different value that goes in there, right? And then if there's more than one instance of the a sub k, then you would apply it to all of them. Good, good, good. Okay, so here's some easy examples. Find each sum. And so just expanding these. So for part A, we want to get 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, right? That's what this is. And I know to stop there because this tells me to stop when it equals to 5, right? So replace the k by a 1. I got a 1 squared. Plus, replace the k by a 2. Replace the k by a 3, and so on and so forth. Oops, I guess I don't need that. So now we just simplify it and get an answer. So this becomes 1 plus 4 plus 9 plus 16 plus 25. Good. So let's see, that's going to be 5. 5 and 5 makes it 30, 39, 45, 55. Good. Okay, for B, well, it doesn't start off at 1, it starts off at 3. So this would be 1/3 plus 1/4 plus 1/5, and that's how I know where to stop, right? And notice that the index in this case was a J, not a K, so we have to be careful about what letters we use. Okay, common denominators here. Let's see, it looks like it's just going to be a multiplication of all of them, 60. Good, so 3 times 2 times 5. Yep, 60. I don't know. Okay. So multiply this by 12 over 12. Multiply this guy by 15 over 15. Multiply this guy by 20 over 20. So we'll get 20 over 60 plus 15 over 60 plus 12 over 60. Good. That's 3547 over 60. Questions, 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 questions? Okay, C says to start off at 5, so it'll be 5 plus 6 plus 7 plus 8 plus 9 plus 10. Start off at 5, end at 10, and all I'm doing is replacing the k index value by a 5. Good, so that's 11, 18, 26, 35, 45. Good. Good, 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 good. D is a little tricky because there is no index, right? Here is the index I, and there is no I. So what we do with that is that, well, when I equals to 1, we just get a 2. Plus I equals to 2, well, we just get a 2. When I equals to 3, well, we just get a 2. Right? We have to add all of them, and we know we keep going until I equals to 6. Right? So this is I equals to 1, I equals to 2, 3, 4, 5, and 6. So this is going to be 2, 4, 6, 8, 10, 12. Any questions? Should have put them here. So this one we got was 55. This one we got was 47 over 60. This one equals to 45, and this one equals to 12. Good? Questions, 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 questions? No. Let's see if the author did the same thing.
I go over C again, please.
Sure. Let's go over here. Oops. Over C, you said? C is this one. So it's the Riemann sum starting at 5 through 10 of this, which is just K. So the first one comes by replacing the K with a 5, plus, then a 6, plus, then a 7, plus, then an 8, plus, then a 9. So we start at 5 and at 10, and we always add them, right? Because that's what this sigma notation is telling us to do. So I just had to add all of these, unless there's something wrong with the summation. That's 11, 20, 30, 37, 45. Yeah, I think so. Good. And is it okay with D? I think D is the trickiest one, right? Because there isn't even an index there. So like, what the heck do I do? There is no I, right? So what we do by default is just add the constant that's there.
So for D, we just go ahead and just use the, I guess, the 2 there 6 times.
Correct. Mm-hmm.
Thank you.
Good. Okay, here. So let's see what the author did. Probably the same, hopefully, unless I did something wrong. Okay, so for A, right, we're replacing the K value with 1, then 2, then 3, then 4, then 5, right? And every time we were squaring them, so we get these. Good. And then we get that. And then for B, we start off at 3, so it's going to be 1/3 plus 1/4 plus 1/5. And here's C and here's D. Good. Okay, graphing calculators for this, I don't worry about that. How about one more example that's a little more complicated, just to point out how that expression is given. So let's say that we have an expression and we want to use any number. You know, n is also very popular. So let's say n goes from 3 through 7. And the thing is that this index value can happen more than once. So I wish there was an example that had more than one of them. So for example, it could be that it is 1 over n plus n squared, for example. So this is letting me know that I want to do 1/3 plus 3 squared. That's when n equals to 3, plus 1 over 4 plus 4 squared, plus 1 over 5 plus 5 squared, right? So we just keep going with these summations. Summation, summation, summation. At each one of these little intervals, we're replacing the index, in this case the letter K, the index variable n, with a 3. And then we just keep going, and we don't stop until we get to the stopping value there, which is equal to 7 in this case. So we gotta include a 1 over 6 plus 6 squared, and then a 1 over 7 plus 7 squared. Good. Sometimes, just to kind of explore more on this notation, sometimes it might not be a pretty little number where it ends. They might just give you some other letter there. It ends at, K or something. All right, well then, if you just want to explore this and expand it, you would say this, but then you would leave a kind of a dot, continue in this pattern, dot, and then continue in this pattern until you get to the stopping point, which is K. So you'd say this. right? That would be this one. There's a plus there. Good. Okay. All right, but let's go back to it being a number. Okay, so let's go back to this being some number. So let's say that it's just equal to 6 again. So let's say it's just 6. Okay, so let's just erase these guys. The other thing that kind of confuses people is there might be another letter in here. Like there might be an X. Okay, all right, well then leave it alone. The index is only referring to the letter N, so if there's an X in there, then just leave an X right in there. Good. So then, I mean, we could simplify this just a tiny little bit. 1/3 plus 9x plus 1/4 plus 16x plus 1/5 plus 25x plus 1/6 plus 36x, right? So if there are other letters running around in there that are not using this little index guy, then just leave them alone. Good. Questions, 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 questions? No. No, no, no. Okay, I think that that's all we have here for this. Okay, so we can use technology to do some work with these, but I'm not going to cover that. I don't think you really need it. So let's just move on past it. Okay, some properties of sigma notation, right? So if we are doing the sum of a sub k plus b sub k, like this, there's two different sequences indexed by k, and notice that the index of the summation is a k, then we can find them separately and then add them together, right? That's what this is saying. Same thing if we're subtracting them. If we're subtracting two of them, then we can do them separately and then find their difference. And this last one is saying if there's a constant that we're multiplying by all our a sub k values, then we can factor out that constant. Good, good, good. So what this means, let's do an example for number 1. So like for number 1, as an example of what that's saying. Let's say I'm asking you to do the sum of k. Man, this thing is not happy now. Why are you so upset? Number 1. Let's say that I want to do the sum as k goes from 3 through k goes to 5. It's just 3, 4, 5, just a few values. And I have some formula in k, like k squared plus, I don't know, square root of k. Say I have that. So this can be broken down by number 1. This is saying that what you could do is separate this as this one. K squared. So find the answer to this plus, and then separate from that, and that 50 is in the terrible spot, k equals 5 and k equals 3 of square root of k. Right? That's what this is saying. If you have a really complicated statement separated by an addition or a subtraction, then you can separate these this way, right? Same thing happens if instead we have a subtraction there. Well, you can just replace it by a subtraction there. Good. 1 and 2. And then the last one says that if there's a constant in there, we can just pull out the constant. So the third one is saying, for example, that if I have this, I don't know, k squared, but I also have a 7 there, summation as k goes from 2 through 9. So I'm going to do k equals to 2, k equals to 3, k equals to 4. Okay, so that one is saying, well, there's this constant here that we're multiplying, so we can just put it on the outside and then figure out what this is. K squared, as k goes from 2 to k equals 9. Figure out what this is, multiply by the 7, and you'll get the same result as this one. Good? Questions, 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 questions? No, 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 no. Okay, sequences and series, chapter 12, section 2. We're going to look at arithmetic sequences. Okay, so as I said before, a sequence is just a list of numbers. There doesn't have to be a pattern. But if there is a pattern, then more interesting things can happen, right? So there's a couple of very common patterns that we look at. One of them is arithmetic sequences. That's section 12. Chapter 12, section 2. And the other one is geometric sequences, which is the next section. Okay, so in this section, we'll look at arithmetic sequences. We'll describe them, define them, we'll use them, and then we'll also find the partial sums of arithmetic sequences. Okay, so what is an arithmetic sequence? So an arithmetic sequence is a sequence that fits this pattern. So let me zoom in a little bit more here. Perhaps the simplest way to generate a sequence is to start with a number a and add a fixed number constant d over and over and over again. So it's a sequence where the pattern from one term to the next is very, very simple. It's just that we add something to it. So for example, let's say that we just start with the number 5. That's the starting value, a sub 1. And then to the next one, we add 3. To get from 1 to the next, we add 3. So let's say that one's 8. And then to get to the next one, we add 3 again. So that's going to be 11. And then we add 3 again. So then that next one's going to be 14. Right? So here is a very simple arithmetic sequence where we go from one to the next, we add 3. To get from this one to this one, we add 3. Right? So we always add 3 to get from one to the next, to the next, to the next. Okay? All right. Now, if we tie them all down to that initial value, then this guy, the 8, is a 5 plus a 3. Let's change it from this. The 8 is the 5 plus a 3. Good. And then tying it back down to that initial value, the 11 is really a 5 plus 2 copies of 3. 3 plus 3. Right? 1 copy, 2 copies. And then the next one on the list, this 14, again, tying it back to that initial value, is a 5, and then plus 3 copies of 3. 1, 2, 3. 3 copies of 3. Good? Okay, so then we can rewrite this as, so let me write this thing. So a sub 1 is just equal to 5. A sub 2 is equal to 5 plus 3. A sub 3 then is equal to 5 plus 2 copies of 3. A sub 4 is a 5 plus 3 copies of 3. Right? 1, 2, 3. And so following that same pattern, I can see that the next one is going to be 5 plus 4 copies of 3. And just to make the whole thing pretty here, let's just add a 1 here. 1 times, let's erase that. That would make it pretty. 3, and then it's a 1 times a 3. 1 copy of 3, 2 copies of 3, 3 copies of 3, so on and so forth. So what's the pattern between the indexed value 2 and here, right? So to find the second one on the list, we start with the initial value and add 1 copy of 3. To find the third one on the list, we start with the initial value and add 2 copies of 3. Right? So the relationship between this number and this number is that this one is always 1 smaller than that one. Good. So following that same pattern, as I keep going and I say, okay, let's find the nth number, I know it's going to be the first, tying it back down to that first value, plus, and then some multiple of 3. And the relationship we've been establishing here is that when this is 5, this is 4. And this is 4, this is 3, right? It's always 1 less. So if this is n, this is going to be n minus 1. Good? Good, 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 good. Any questions, any questions, any questions? No? No? Okay, so we, in general, like to call this the a sub 1 value, just a, which is the initial, the first term of our sequence. And then we call this the common difference, right? The common difference. Common difference. And we often use the letter D. So in general, we get this little formula right here. Right. A is that initial amount. In my little example, just using this as a little example, for me, A was equal to 5. And the common difference, D, is this 3. I'm always adding 3 every time. Good. So I can express my arithmetic sequence this way. A, and then A plus a D, and A plus 2 Ds, and then A plus 3 Ds, or I can express it with this formula. Any questions about that? No? Good. Questions, questions, questions? Okay, so the number D is called the common difference because any 2 consecutive terms in the arithmetic sequence differ by D. Right? Any 2 consecutive numbers differ by the value D. An arithmetic sequence is determined completely by the first term A and the common difference D. If you just know those 2 things, the first term and the common difference, you can completely expand out the whole sequence by knowing those 2 things. And you can write down the formula, right? The closed formula for it, because all it needs is A, the initial value, and D, the common difference. Okay. Thus, if we know the first 2 terms of an arithmetic sequence, then we can find the formula for the nth term, as the next example shows. Okay, so let's look at this example. Find the common difference, the first 6 terms, the nth term, the 300th term of this sequence here. Okay, so this is a given sequence, so we know that the first value, A sub 1 is that guy, A sub 2 is a 7, A sub 3 is a 1, A sub 4 is a negative 5. And so the A in our formula is A sub 1, and that's a 13. Right? So we know the first value. And to find the common difference, all we have to do is take any 2 consecutive values and subtract them. So the common difference in these is a negative 6. So it's 7D is equal to 7 minus 13. So D equals to negative 6, which we would have gone by any other 2 consecutive numbers. 1 minus 7 can also give you D. So D still gives you negative 6. Right? Any 2 consecutive numbers, you subtract them. Notice that in the sort of more traditional case that we had before, when I was adding 3, they were going up. Okay. I was growing by 3. It's always plus 3, plus 3. So here I would have gotten my common difference by taking 8 minus 5, or 3. Or I could have gotten my common difference by taking 11 minus 8, or 3. So it has to be in that order. Right? 1 minus the one that came before it, right? And that gives you positive growths. But notice that in this example, we get a minus, and that's because it's decelerating. They're getting smaller. They're growing toward the negative direction. Right? So we're getting negative D. Okay, so now we have everything we need. The formula for this sequence was A plus n minus 1 D, right? So for us, a is equal to 13 plus n minus 1, and then d is equal to negative 6. So here's our closed formula for this sequence right there. We can manipulate this a little bit, put this out in front, make it a subtraction. So it might look a little nicer if we write it as 13 minus 6 times n minus 1. Let's check to make sure that it works out. For the last one, we know for sure. Check. So when n equals to 4, we better get a negative 5. Okay, so a sub 4, a sub 4 should be equal to 13 minus 6 times 4 minus 1. Okay, so that's going to be 13 minus 6 times 3, which means that a sub 4 is equal to 13 minus 18. Means a sub 4 equals to negative 5. Yep, just what we expected. So the formula seems to be working out. Good. So find the common difference. The first 6 terms, okay, so it's asking me for a sub 5 and a sub 6, and the 100th term. I'm sorry, the 300th term. Okay, so now that I have that formula for it, and a sub 5 is going to be equal to 13 minus 6 times 5 minus 1. A sub 5 will be 13 minus 6 times 4. A sub 5 is going to be 13 minus 24. A sub 5 is going to be equal to negative 11. Good, 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 good. The other way I could get it is by pointing out that the common difference is minus 6. I'm always subtracting minus 6. So if I know the fourth one, right, going on this list, this means I subtract 6 every time. So minus 6 gets me to minus 11, and I know that minus 6 is going to get me to minus 17. Right, so just knowing that I'm subtracting 6 every time, I can easily conclude that the next one is minus 11 and then minus 17. Or I can use my closed formula. Let's use the closed formula one more time. A sub 6 is going to be equal to 13 minus 6 times 6 minus 1, which means it'll be 13 minus 6 times 5, which means it'll be 13 minus 30, which means it'll be negative 17, just like I had suspected. Okay. So far I have that we have our list, our sequence. Does it have a name? 13, 7, 1, 13, then 7, then 1, then minus 5, then minus 11, then minus 17. Right, so here is my first few values of my sequence. I'm subtracting 6 every time, or adding a negative 6 every time. Right, since technically we're doing a summation. It's just that we add a negative number every time. Okay, but now the next thing they wanted was to find the 300th value. We found a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, dot, 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 dot. But now they want a sub 300. These we could have easily gone by just subtracting 6 every time. But then to get to 300, that would take forever, especially if you don't have technology to subtract 6 every time, all the way until you get to 300. So that's not a very efficient way to do it. Luckily, we do have this formula, right? So using the formula, we can just plug it right in and get our answer fairly easily from there. Right, so now a sub 300 is just equal to 13 minus 6 times 300 minus 1. Good. So a sub 300 is equal to 13 minus, what's that going to be? 299. 6 times 299 So that should be 1,794. I think. We have a. No, use my phone. Let's see. We have 299 times 4. Ah. Okay. 299 times 6. Okay. Oh yeah, cool. 13 minus 1794. Yeah, 1781. Minus 1781. Good, so that's what goes here. Minus 1781. Any questions? No? No? No questions? Let's see what the author did. Common difference is minus 6. Plug it into our formula. Yep, that's what we get there. And then we can get the first few numbers quite easily. We just subtract 6 every time. And then when we plug in 300, we get to this. No questions. Good, good, good. Okay, but what if they don't give us 2 consecutive terms? They don't give us the first 2 terms. They just give us any 2 terms. Now the questions get a little bit more fun. So here's another example. The 11th term of an arithmetic sequence is 52, and the 19th term of the sequence is 92. Find the 1000th term. Okay, so kind of visually, let's kind of create what this is saying. So here's a sub 1, which they didn't give me. There's a sub 2, they didn't give me that one. They gave me the 11th term, so dot, 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 way over here. They gave me the 11th term of my sequence. Stop it. The 11th term of my sequence, they said that one was a 52. And then dot, 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 they gave me the 19th term of the sequence, which is a 92. Good. Dot, 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 dot. And their question is, find the 1000th term of the sequence. Good. Okay, so another key thing is that they did tell us and it's an arithmetic sequence. So by knowing that it's an arithmetic sequence, I know that this is the formula for it. Okay? It has to fit that. And that's where A is A sub 1 in the arithmetic sequence. Right? So A sub 1 is the same thing as A. Okay, so our mission, if we choose to take it, is that we need to figure out what this is. If we can figure out what A is, and we can figure out what D is, we'll get our closed formula for it. And once we have our formula for it, we can come back over here and plug in n equals to 1000 into there, and we'll be able to get our results. Good. Okay, so from this, I can get that when n was equal to 11, n sub 11, n sub 11 is equal to that initial value, which we don't know, plus, and then this guy was 11 minus 1, and then a common difference d, which we don't know. Good. So the output of this whole thing was 52, so we should get that 52, right? That's what this is. The 11th number on my list is 52. 52 is equal to A plus 10D. Okay. From here, then we get that the 19th term is equal to A, an unknown value, plus 19 minus 1 times the common difference D, which we also don't know. And so this is going to lead me to 92 is equal to A plus 18D. Good. So what we have here is a system of equations. So we have 52 is equal to a plus 10d, and we also have 92 is equal to a plus 18d. Good. Good, good. The way I'm going to solve it is by the elimination method. So I'm going to add these two equations, but I want to first manipulate them a little bit such that when I add them, one of the variables disappears. And since I just have a positive a here, it makes sense to multiply this equation by, so let's call this equation number 1 and equation number 2. So I'm going to take equation number 1 and multiply it by -1. That way I get a minus a there. Okay. So I'll get a negative 52. Negative 52 is equal to negative a minus 10d. Right, after I just distribute a minus through all of these. And then I'll get a 92 equals to a plus 18d. Now I'm going to add these guys. When I add them, this is just going to give me a 40 equals, these guys cancel, equals 8d. And now I can divide both sides by 8, and 40 divided by 8 equals to d. So the common difference d equals to 5. Good. So one down, one to go. And once you have one of them down, then you can go into your either one of your statements, equation 1 or equation 2, to solve for the other one. Okay, so now that I have that, I'm going to go back to equation 1. Plus 10d, but now I know that the d is actually a 5. Right, plugging this d into there, squeeze this up here a little bit, I get that 52 is equal to a plus 10 times 50, and 10 times 5, which is 50. So 52 equals to a plus 50, so therefore 52 minus 50 equals to a equals to 2. Now I got everything we needed, right? So coming back up here, this must be a 2 and this must be a 5. I have my formula. A sub n equals to 2 plus n minus 1 n minus 1 times 5. Good. Questions, 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 questions? Zoom out a little bit. Or too much. Any questions on any of that? No? Very good. Okay, so now that we have our formula, now we can answer the next part of it. Once we have our formula, we can find the 1,000th term. Right? So now a sub 1,000 is going to be equal to 2 plus 1,000 2 plus 1,000 minus 1 times 5. Good. So if I distribute this 5, it'll make the whole thing a little easier. It's 2 plus, and then 1,000 times 5, that's just 5,000, minus 5, that's 4,995, plus 2, 4,997. Good. So that's the number that goes right here. That's the answer to our whole thing. 4,997. Good. Any questions? No questions, no questions, no questions, no questions. Good, 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 good. Okay, all right, let's see what the author did. Same thing, they set up a system of equations. 52 equals to a plus 10d, 92 equals to a plus 18d. Solved it, and they get, okay, he just said solve the system. So you get a equals to 2, d equals to 5. So you get the same closed formula, 1,000 leads you to that, and that's how we get our answer. Okay. Any questions at all? No. Okay, so sometimes you'll be given a arithmetic sequence or asked to expand it or find a particular value. Sometimes you're given the sequence and you're told it's an arithmetic sequence, find the formula, like we just did. And then another thing that we might be asked to do is to find the partial sum of an arithmetic sequence, like sum the first 10 of them or sum the first 100 of them, something like that. And you can always just do it by brute force and actually just add them all. But we want to establish patterns to make life a little easier. So, for instance, let's say that you're given the task of adding the first 100 numbers, 1 plus 2 plus 3 plus 4, all the way up to 100. So we can express that using a Riemann notation like this, right? So we want to add the first 100 values. This is a very famous example that was given to a famous mathematician named Gauss when he was just a little kid. I think like in the first grade or something like that. He was a brilliant guy. So his teacher thought this was going to be a really tedious, long kind of thing, and little brilliant Gauss figured it out in no time, and became famous. So how did he do it? How do you find, what's a nice little shortcut for finding the sum of the first 100 numbers? So let's think of it this way. We want to find this, right? Find the sum s, right? That's what we want. And it's going to be 1 plus 2 plus 3 plus 4 plus 5, and dot, dot, dot. Keep going, right? Dot, 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 dot. Way at the end over here, we have the 96th term plus the 97th term plus the 98th term plus the 99th term plus 100, finally, right? Okay, so that's what we want to do. We want to find s, which is equal to the sum of all of these numbers. Okay, well, how about if we also consider s just written backwards? 100 plus 99 plus 98 plus 97 plus 96 plus dot, 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 right? And then going backwards, the last one would be a 1. Right before that would be a 2. Right before that would be a 3. Right before that would be a 4. Right before that would be a 5, and so on and so forth. Right? There would be 100 numbers there, and so 100 numbers here, right? Because they're just written in reverse. Okay, so now if I add both of these two things, on the left-hand side, I would get twice the s value, right? Like let's say this whole sum adds up to, I don't know, 49,000 or something, I don't know, whatever, some number. Then if I add this plus this, that would be twice as much. Good. Like let's say it adds up to 4,000, then adding these two would add up to 8,000. Good. Okay, now on an individual term-by-term basis, this is where something interesting happens. The 1 plus the 100 adds up to 101. Good. Plus, and then the 2 plus the 99 adds up to 101. Good. And then the 3 plus the 98 adds up to 101. Right? So in every single case, they always add up to 101. And same thing at the end here. 96 plus 5 adds up to 101. And 97 plus 4 add up to 101. And 101. And 101. And 101. Okay? Okay. Well, a shortcut of a long addition like this is to figure out how many are there and multiply that times 101, right? So all of this right here, all of this is 100 copies of these, right? Because remember, each one of these led to a 101. So this is 100 copies, 100 copies of 101. Good. So all of that can be simplified as follows. This is equal to 2 times s equals to 100 copies times 101. Any questions about that? No? No? And so now s can be found by dividing both sides by 2. Let's take, well, I'll do it in another step. Divided by 2, divided by 2. So we get 2s there, 100 and 101 there. And so s, I'll put it here, s equals to 1/2 of 100 times 101. Good. Questions, questions, questions? So this is just going to be equal to 50/50. So here's little Gauss figured all this out in first grade or something. Figured out that instead of actually adding 1 plus 2 plus 3, right, plus 4, that that would have taken a very long time to add up all 100 numbers that way. But there's a nice, pretty little shortcut to it. Any questions? No? No? Okay, so this was just a simple example where we just want to add the first 100 numbers. But what if we want to apply the same idea, the same pattern that he did in general to any arithmetic sequence? So we want to follow the same technique to be able to figure out a general pattern. So I'll put in general. Given any given any arithmetic sequence, sum the first n values, sum the first n values. Okay, so if it's any arithmetic sequence, we know that the formula is going to be this. Okay, n-1 d. Right? So if we want to expand the first n numbers of my sequence, it would be a is the first one, right? And then it's going to be a plus d, and then it's going to be a plus 2d, and then it's going to be a plus 3d, dot, 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 dot. And then the last one on there is going to be a plus n minus 1d. Good. Okay, so if I want to find the sum of the first n of them, I want to find that sum right there, all of those right there. Just like before, we want to apply this technique. Let's write them all down in this direction. So I want to do a plus, now I want to do a plus d, plus, next I want to do a plus 2d, and you know what, let's put them in parentheses so that they look a little better. That one, and then that one, too many plus signs running around. And then the next one is going to be a plus 3d, and then the next one, dot, 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 dot. And I want to go all the way out to that last one over there. And the last one is going to be a plus n minus 1d. Right? Well, what came right before it? So notice that the pattern here is that, okay, well, we have the initial value, but then we have one copy of d is the second one on the list. The third one on the list is 2 copies of d. The fourth one on the list is 3 copies of d, and so on and so forth. So the nth one on the list is n minus 1 copies of d. The one that comes right before it is going to be a plus n minus 2d. And the one that comes right before that is going to be equal to a plus n minus 3d. Okay. Any questions about that? No? No? Okay, just following advice, then we're just going to rewrite the exact same list, but in reverse order. So the last one on the list is going to be a plus n minus 1d. Come on. N minus 1d plus the one that came right before that. So this is the last one on my list. The one that came right before that would be a plus n minus 2d. The one that came right before that would be a plus n minus 3d. Good. And the one that came right before that would be a plus n minus 4d, dot, 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 until the very last one. Okay, going in this direction, that last one would have been a. And the one that came right before the very last one would be a plus d. And the one that came right before that would have been a plus 2d. Good. Okay, so now following the same pattern as before, we're going to add all of these up. And so I end up with twice as many as the s sub n's as I want, the sum of the first n values. So I add them up, and I get that. Okay, and so what happens with these? Let's add these two up. So if I add these two, well, we add the common terms. It's just going to be a plus this. So that first term is going to end up being a plus n minus 1d. Good. So all of this ends up being 2a plus n minus 1d. That's this first term. These first two being added. I'll give you this. Good. Next, we want to add the next two terms. Plus, and now we want to add this one and this one, right? We want to add these two, and that's going to lead to this next summation. So that's going to be a plus d, and we want to add to it plus a plus n minus 2d. Good. Again, we combine like terms, so that's going to give us 2a. And then we have d plus n minus 2d. Good. And these, if we factor out a d, we end up with 1 plus n minus 2 times d, 2a, plus all that. And so these simplify to give me 2a plus n minus 1d. Oh, same thing as that one. Good. We'll do one more just to show that it always works out. So these two give you this one, these two give you this one, and then this one plus this one. I'm going to add these two and I'll put them over there. I have a plus 2d, and I want to add to it a plus n minus 3d. Right? So again, you combine like terms, we get a 2a for sure, 2a plus, and now we end up with these. So I end up with 2d plus n minus 3d. Okay, again, if I factor out a d from these, I get a 2 plus n minus 3 and multiplied by d plus 2a. So I get 2a plus n minus 1d, exactly the same thing as before. Right? So these two give you 2a plus n minus 1d. These two give you 2a plus n minus 1d. These two give you 2a plus n minus 1d. And that'll happen all the way along the line. Just like in the previous example when we did these numbers, they always added up to 101, 101, 101, 101 every time. And how many did we have? Well, in the previous example, we had 100 copies of 101. So what's going to happen here is that we're going to end up with n copies, right? There are n of these, n copies of this. Good. So we're going to be adding all of these. So let me copy that down here. So far what we have is that this 2s sub n is equal to 2a plus n minus 1d plus another copy of 2a plus n minus 1d plus another copy of 2a plus n minus 1 times d. Right, that's what these are. These are coming from here. This green one was the result of that guy, and well, I guess. This one was the result of that. The green one was the result of that one, and then the blue one. So I just did the first three, but then we could keep going, and then you could see that obviously the last one is going to be really easy. The last one is just going to be this. So we'll say plus dot, 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 keep going, and the last one is just going to be a plus a, that's 2a plus n minus 1d, plus n minus 1d. Again, the exact same thing. So we have 2a n minus 1d 1 time, 2 times, 3 times, oh, d, got the d in here, n minus 1d. N minus 1d. Okay, and so we have n copies of this. It's a sum of n copies of 2a plus n minus 1d. So twice S sub n is equal to n times 2a plus n minus 1 d. Good. So just like before, we divide both sides by 2, divide by 2, divide by 2, and we're almost at our formula. The sum of the first n values of an arithmetic sequence is equal to n divided by 2 times 2a plus n minus 1 d. That's one of the given formulas for it. Or the other thing we could do is expand this out a little bit and say that if we expand it, we can rewrite it as S sub n is equal to n over 2. And then I'm going to rewrite this as a plus n minus 1d, since 2a can just be written as a plus a. Okay. And then this is the formula for the nth value. It's the last term. This is a sub n. Good. So this is S sub n equals to n over 2, and this is going to be a plus a sub n. That's the other way that this formula is given. Good. Good, good, good. So meaning that this is the formula, the closed formula for the underlying sequence, but it also represents the last value in the sequence that you're trying to add. So if you know the first term and the last term, and how many terms there are, then you can find the sum of all the values. Any questions? No? 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 No, no, no? Okay. Let's see what your author did here. Okay, same kind of thing. So if we want to find the first n values, the sum of the first n values of a given arithmetic sequence, here they are. Here's the first term, the second term, the third term, the fourth term, so on and so forth. This is the nth term, right? Yes. And now if we want to add them all up, well, looks like he didn't really go through the process of doing it, but we end up with the same formulas. Right, so it's 2a plus n minus 1d times n over 2, or that can simplify into this, which is given in a nice little table for you to use. For an arithmetic sequence, and be careful that this formula only applies to arithmetic sequences. For an arithmetic sequence given by a sub n equals to a plus n minus 1 over times d, the nth partial sum, S sub n, right, the sum of the first n values of your arithmetic sequence, is given by one of these two formulas, which they're both equal to each other. It depends on how you want to memorize them. And sometimes one is easier to apply than the other, depending on the initial conditions given to you. Okay, so for example, find the sum of the first 50 odd numbers. Okay, so let's do this. Find the sum of the first 50 odd numbers. Okay, so here they are. Here's 1, 3, 5, 7, 9, 11, dot, 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 dot. So far I have the first one, the second one, the third odd number, the fourth odd number, the fifth odd number, the sixth odd number, right? So don't confuse the actual value with this, right? This is indicating that we want 50 numbers, not that we want to reach up to the value 50. That sometimes confuses people. Anyway, so we want to keep going until we find the 50th odd number and then add them all together. That's what we want to do. Good. Because they're the odd numbers, we already know, we've been working with this thing, we know that the formula, the closed formula for odd numbers is this one. Right? So if we let n equal to 1, we get to 1. If we let n equal to 2, we get to 3, right? And so on and so forth. So from here, I can find out some more information. I know that the 50th odd number is going to be 2 times 50 minus 1. So the 50th odd number is going to be 99. 99. Okay, so the sum of the first 50 odd numbers is really the same thing as this. S sub 50 equals to 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus dot 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 all the way out to well, the last one is 99, but the one that came right before it would be 97. The one that came right before that would be 95. Good. So that's what we want to find out, the sum of all of those. So we already know Gauss's little trick. We could do it in reverse, put a 99 here, 99, 97, right? And it looks like in this case they would all add up to 100, right? His little trick of saying, well, let's double that. Let's rewrite this in reverse. That would be 99 there, plus 97, plus 95, plus dot 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 dot. And we know this ends in a 1 there, and a 3 there, and a 5 there. And we know that his little trick is to add these. So that was 100 plus 100 plus 100. They always add up to the same thing. Dot 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 dot. Plus 100 plus 100. And we know that there's going to be 50, right? This is the first 50 numbers. There's 50 of them. So we know that this is going to be equal to 50 copies of 100 being added. So if we add them together, we'd have twice as much as what we want. So twice S sub 50 would be equal to 100 times 50. And so S sub 50 would be equal to 1/2 of 100 times 50. Okay, that's kind of doing it by hand and reinventing the whole wheel. That's why we went through the trouble of doing it in general so that we can just use our nice, pretty little formulas for it, right? So this is sort of the brute force method following his pattern. But also we have this nice little formula. The sum of the first n values is given by either this formula or this formula. We can follow either one. So one of them is that it's n over 2, 2a plus n minus 1 times the common difference d. Okay? And so we have everything we need to be able to figure out the answer for when n equals to 50. The first 50 numbers is going to be equal to 50 over 2 times twice the initial number, which was 1. Right? This is for us, a equals to 1 from there. And the common difference, well, that's easy to tell. The common difference is going to be to always add 2. So d equals to 2. Okay? So plugging it into here, we get this. We get 50 minus 1 times 2. So S sub 50 is going to be equal to 25 times, and this is going to be 2 plus 49 times 2 is 98, which gives me S sub 50 is equal to 25 times 100. And I can already tell that that's going to be the same answer as this one. If I do half times 50, that's 25, 25 times 50. Or S sub 50 is going to be 25 hundredths. Good. Same thing as before when we did it the brute force method over here. It's 2500. Any questions so far? So we did it the hard way there. We can use the first formula, and we can also use the second formula given. Either one is fine. The second formula for the sum of the first n values is equal to 1/2 a plus a sub n. Right? Oh, no, times n. n times a plus a sub n over 2. That's the other formula for it. And so for us, if we have the 50th one, we want to find the sum of the first 50, then we multiply 50 times the first number of my sequence, which was a 1, the last number that I want to figure out, which is plus a sub 50, a sub 50, the last number in the sequence, all divided by 2. So s sub 50 is equal to 50 times 1 plus 99, right? 99 is the last number in my sequence. This is a sub 50, right there, a sub 50. And the whole thing divided by 2. So I'll get 100 divided by 2, which will give me the same answer, 2500. Same answer. Okay, any questions? Questions? See what the author did. Okay, same thing. They found the closed formula for the arithmetic sequence, and then they used that formula to figure out the 50th value on the list is 99. And then you can just use one of the formulas. So they went with this formula. This is the formula of the general formula of S sub n is equal to n times a plus a sub n all over 2. Okay. So a sub 50, the 50th value, the last value is 99. A sub 1 was just 1. And so that gets us to the same answer as before. Any questions? Okay, so very important, don't forget that this formula only applies to an arithmetic sequence, right? The partial sum of an arithmetic sequence,